All right, so today's lesson is going to be over beta decay. So we had that session where we sort of briefly introduced the different modes of radioactive decay. We talked about alpha, beta, and gamma decay. And then last session, we went in a little deeper on how alpha decay works, and we reviewed a little bit. So today we're doing the same thing, but with beta decay. Our learning goals are to again review beta decay and the two main types, which are beta minus and beta positive. So we'll talk about the differences between those and how to set up those decay equations. And then something we didn't go into last time is what the neutrino actually does. So today we'll look to understand the role of the neutrino and why it's necessary to conserve energy and momentum. And then we'll also introduce something called electron capture and talk about the differences between it and positron emission or beta positive decay. And then at the end, we'll explain how beta decay can change the identity of an element and the effect that it has on nuclear stability. So the first warm-up question is what is emitted during beta minus decay? And like the name of the decay mode implies, when we have beta minus decay, a beta minus particle is released. And remember that a beta minus particle is the same thing as an electron. Those are two different names for the same thing. So similarly, if we had beta plus decay, we know that a beta plus or a positron is emitted. The next question, what happens to the proton to neutron ratio during beta plus decay? Recall that the difference between beta minus and beta plus decay is one of them is a proton converting to a neutron, and the other is a neutron converting to a proton. And in both of those cases, there is a change in the amount of charge in the nucleus, and the particle that gets emitted sort of acts to balance out that change in charge. So if we have a neutron turning into a proton, we gained a positive charge. So in order to cancel out, we have a negative charge as well. So this negative charge is an electron or a beta minus particle. And if we did the opposite direction where we have a proton turning into a neutron, we lost a positive charge, so we have to add one to balance things out. So notice that this is going to be in the form of a beta positive or a beta plus particle or a positron. So if we're looking at beta plus decay, we're looking at which one of these involves a beta plus particle getting emitted. So it's this lower one here. And since this involved a proton turning into a neutron, we know that the proton to neutron ratio got a little smaller because that ratio is the number of protons divided by the number of neutrons, and the number on top went down, the number on bottom went up, so that fraction gets a little smaller. And then, of course, if we wanted to look at beta minus decay, where this thing that gets emitted is a beta minus particle, in this case, we gained a proton and lost a neutron. So the fraction or that ratio gets a little bit larger. And we'll bring this idea of proton to neutron ratio up again a little bit later. Call, we have that valley of stability on the proton to neutron graph. So whether the ratio increases or decreases doesn't necessarily say anything about the stability, but whether that ratio approaches that valley of stability does tell us something about it. And again, we'll talk about that later after we're done reviewing and introducing a couple of new things. So the last warm-up question is, what is the difference in atomic number before and after a beta decay? So if we wanted to find the exact difference, we would have to know whether it's a beta plus or a beta minus decay. But in both cases, we know that the atomic number or the number of protons is going to change by one, plus or minus one. So in beta plus decay, we lost a proton, so the number goes down by one. And In beta minus decay, we gained a proton, so the atomic number goes up by one. And then recall that the mass number, which is the number of protons and neutrons, stays the same because we're not really gaining or losing protons out of nowhere, but rather they're undergoing proton to neutron reactions, and so they're just changing between one another. So again, the mass number is conserved. So with that review on beta decay out of the way, we can go into more detail on neutrinos. So remember last time we talked about neutrinos a little bit and we sort of tacked them in at the end of the beta decay equations. And I mentioned that they played a role in conserving energy and momentum, but we didn't really go into any more detail on it. And I kind of said, don't worry about it. So I just have a couple of diagrams here to hopefully explain a little better what's going on. So early on, when people were conducting experiments with beta minus decay, it was odd that when a nucleus went under that decay, energy and momentum didn't seem to be conserved. It seemed like just a little bit of that energy and momentum was missing. So it was as if there was something, some invisible force or something that was taking away those missing quantities, but it wasn't something that we were able to detect or measure. So it seemed like the conservation of energy and momentum were being violated, which tells us that something's wrong because we say that that can't happen. So you can see this nucleus undergoes beta decay in this picture here, where we have this starting nucleus or parent nucleus, and then this daughter nucleus. And if you look closely, you'll see that one of the neutrons changed into a proton. So if we gained a proton, what type of beta decay is this? Or in other words, what gets emitted? Since we gained a positive particle, we know that it must have emitted a negative particle. So this is an electron or a beta minus particle. So this is beta minus decay. And so again, when a nucleus undergoes this process, if we were to add up the energy and momentum here with just the parent nucleus and then add it up here with the daughter nucleus and the electron, we would notice that a little bit of energy and momentum is missing. So in 1930, I believe, Wolfgang Pauli posed that there must be some very small particle that was carrying away this energy and momentum. And at first he called it the neutron, but of course now we call these neutrally charged particles neutrons. So he changed the name to neutrinos. And he said that a neutrino must be neutral, so it doesn't carry any electric charge, and it must be very light, a mass that's very small or close to zero, and it must be weakly interacting. The reason to say that it's weakly interacting is just because we had so much difficulty detecting it, it was almost invisible. If we can't detect it, it must not be interacting with the stuff we're used to dealing with. So I'll write down those three properties on the screen. So the first is that the particles must be neutral, so they don't carry an electric charge. The second is that they have to be light, so they have a very small mass. And then the third is that they must be weakly interacting, which just again means they interact very weakly with other matter. So from this idea that neutrinos interact very weakly stems something called the weak interaction or the weak force. So last time when we introduced neutrinos, I mentioned that they deal with some concepts from quantum physics that we're not really going into. And most of that would fall under the umbrella of the weak force. It's not something that we're going to go into. So it's a sufficient understanding for right now of the weak force to say that all this does is governs neutrinos. More specifically, it changes something called the lepton number of a particle. And without going into what exactly the lepton number means, recall that we introduced two types of electron neutrinos actually. We introduced the sort of regular electron neutrino, and the anti-electron neutrino. So the difference between these two is in their lepton number, which is governed by the weak force or the weak interaction. So recall that when something underwent beta minus decay, it emitted an electron and an anti-electron neutrino. And when it underwent beta plus decay, it emitted that positron and a sort of regular electron neutrino. So up here where we have an example of beta minus decay, we know that there must have also been an anti-electron neutrino that was emitted. And we mentioned last time that, with the negative charge, you have this bar here, and with the anti-electron neutrino, you have this bar as well. So that's how you can remember that these two get paired together. And then when we have a positron, we no longer have that bar present, and there's no bar present on the neutrino either. So that's a very basic explanation of how neutrinos work and sort of how we came up with them. And we'll come back to this again in a little bit when we work out some examples of beta decay. And we'll still just be adding them on the end, sort of like we did last time, but we'll know that this is actually necessary in order to conserve those quantities of energy and momentum. So the last thing that we want to cover before going into those examples is the idea of electron capture. So the first thing I want to know is when beta plus decay occurs. So in beta plus decay, we have some nucleus that we say is rich in protons. So it has a lot of protons. And so of course, beta plus decay turns one of those protons into a neutron. So we have a proton and that gets turned into a neutron. And because we lost a positive charge, we know that this must kick out our beta plus particle or our positron. So we can think of this as one method of getting rid of that extra positive charge that's hanging out in the nucleus due to the excess of protons. That's the method that we're familiar with. Another thing that we can do is if we again have that excess of protons in the nucleus, we can take an electron that's just floating around the outside of the nucleus, is orbiting, and this can happen in an unstable nucleus. The electron gets brought into the nucleus and it gets captured, which is where the name electron capture comes from. So it gets captured, and we now have this proton and electron next to each other, and this actually ends up turning into a neutron. So recall that protons and neutrons are very similar in mass, but the big difference is that the neutron is neutrally charged, whereas the proton is positively charged. So if we cancel out the positive charge of a proton, we're essentially just left with a neutron. So again, we have this process where an electron that's already orbiting the nucleus gets absorbed and it combines with a proton to turn into a neutron. This is another example where the quantities of energy and momentum are not conserved. So we have to tack in an electron neutrino at the end just to balance things out. So if we wanted to write things out in a formal decay equation, we would have a proton plus an electron, right? And these get put together and we end up with a neutron, right? This turns into a neutron. And then we also have an electron neutrino. So notice that earlier when we had an electron on the right side of an equation like this, we would join it with an anti-electron neutrino. And we said that this made sense because, we have bars on each of these, so we're pairing those together. But then if you look at this example, on the left side, we have our electron, you have that bar. But over here, it's a regular neutrino. It's not anti, so that bar is not present. But also notice that these are no longer on the same side of the reaction. They're on separate sides. So it's sort of like if you had a simple addition equation, if you had x plus 1 equals y, we know that this is equivalent to x equals y minus 1. So when this 1 goes to the other side of the equation, its sign changes and it becomes negative. So this is sort of a similar idea where this electron and this neutrino are still sort of paired with one another, but rather than matching exactly, they should match in opposites because they're on opposite sides of the reaction. And so again, just to recap, the reason we have to add on this electron neutrino to the end is because when we observe this process of the electron getting absorbed and this proton-electron pair turning into a neutron, there's some missing amount of energy and momentum that's no longer present in the nucleus. So it must have been attached to this particle we're calling a neutrino that has since been ejected from the nucleus. So again, we started with a diagram of beta plus decay, and we said that that commonly occurs in proton-rich nuclei, and electron capture also occurs in proton-rich nuclei. So we sort of have those two alternative methods for getting rid of that excess positive charge in the nucleus that's making things unstable. Okay, so I have an example written out here, and again, we're talking about electron capture. So we can sort of fill in some of these blanks we have with that model. So we have this parent nucleus here, and because it's electron capture, we must be capturing an electron. So an electron goes right here. So it gets put together with this parent nucleus. And remember that we said this typically occurs in proton-rich nuclei, where we're trying to get rid of the excess number of protons. So in this reaction, we are losing a proton because it's turning into a neutron. So this proton number or atomic number will decrease by 1. And again, it's turning into a neutron, so the mass number is conserved. So I'll pull up the periodic table, and we'll see that if we have 3 protons, our element is lithium. So we have lithium here. And recognize that we have our parent nucleus and our daughter nucleus, and then this electron was initially outside of the nucleus, presumably, orbiting and moving around. So in order to conserve energy and momentum, we have to add something else on the end of this side here, and that's going to be an electron neutrino. And it makes sense that this is an electron neutrino as opposed to an anti-electron neutrino, because remember, we said that electrons and anti-electron neutrinos are paired together, and positrons and regular electron neutrinos are paired together. So looking at this equation where we have, our beta particle on the left and our neutrino on the right, they're on opposite sides, so we would expect them to be opposites. So we have another example of electron capture here. So again, we're trying to get rid of these extra protons, so we lose a proton. So this is going to go down to 18, and our mass number is conserved. So now if we now have 18 protons, that must mean we have argon, which you can get by checking your periodic table. Okay, and this is the electron capture. So on the left side, we have our electron, and then corresponding with that, on the other side of the reaction, we have our opposite electron neutrino. So that's the basic idea of electron capture. I think it's useful to view as an alternative to beta plus decay, and it's another example where we can see the neutrino popping up in decay equations. But since the focus of this lesson was on beta decay, we'll go back to that and work out a few practice examples. And these should sort of be review from last time, but again, we should have a better understanding of the neutrino and why that's there now. So for this equation, we'll start off with boron 11. Okay, and it's going to turn into carbon 11 and something else and something else. So the first thing to do is identify what kind of decay this is. So I'll give you a hint, it's either beta minus or beta plus decay. And notice that we're gaining a proton, which means we're gaining a positive charge. So we want to cancel that out with a negative charge in the form of an electron or a beta minus particle. And going alongside that, we have to have a neutrino to conserve energy and momentum. And because these are on the same side of the equation, we know that this beta minus particle gets paired with an anti-electron neutrino. So the bars match. So again, this is beta minus decay because of that beta minus particle that cancels out the additional positive charge. So we'll go ahead and work out another example. This time we're going to be starting with sodium 22, and that's going to decay into something plus a positron or a beta plus particle and something else. So if we identify the type of decay, we have the beta plus particle. So as the name implies, this is beta plus decay. And remember that we're adding this positive charge here to account for the fact that we lost a positive charge in the nucleus, which means a proton turned into a neutron. So the proton number decreases by 1, and the mass number stays the same. So since we have 10 protons, we know this is neon. The last thing to do is write our neutrino over here, and it's paired with a positron, so we know this will be a regular electron neutrino. Here in this example, we're going to start with magnesium 23. Okay, and this is going to decay into sodium 23 and something else and something else. So the first step is to identify the type of decay. Notice we lost a positive charge, so we have to add an additional positive charge to keep things balanced, and we'll do that in the form of a positron or a beta plus particle. So this is beta plus decay. So again, paired with that beta plus particle is a regular electron neutrino. This one will have carbon 14, and this is going to decay into nitrogen 14 plus something else plus something else. So looking at our parent and daughter nuclei, we see that we gained a proton, so we gained a positive charge. In order to cancel that out, we have to also have an additional negative charge in the form of a beta minus particle or an electron. So paired with that beta minus particle is an anti-electron neutrino. So the next thing we're going to look at is this nuclide chart, which we've talked about before. And we'll ask a couple of conceptual questions just about this graph and how it relates to the different types of decay that we've talked about today. And then that'll be it for this lesson. So the first thing we want to do is talk about how each type of beta decay would shift a nucleus on the chart of nuclides. So this relates to the warm-up questions we started with. Remember, we asked how do beta plus and beta minus decay affect the proton to neutron ratio? So notice based off of the axes of this graph, we have neutrons here and protons here. So the slope of this graph is the neutron to proton ratio. the number of neutrons divided by the number of protons. So let's first look at beta minus decay. So remember in our reaction, we have a neutron turning into a proton. And to account for that positive charge we gain, there's an additional beta minus decay. So this describes beta minus decay. And then when a proton turns into a neutron, we lost a positive charge, and we account for that with an additional beta plus particle. So this is beta plus decay. So again, looking first at beta minus decay, we lost a neutron and gained a proton. So you'd expect this ratio to decrease because the top decreases and the bottom increases. So this value gets smaller. So if we imagine our particle, say here, if we imagine the slope between the origin and our point, we see that this is pretty steep and the slope decreases or becomes less steep. So we would move a little closer to the line of stability down here. So the particle would move in that direction a little bit. And this makes sense looking at the labels of the regions on this graph. You see all of this blue over here, which represents nuclides that will undergo beta minus decay. So again, particles over here, when undergoing beta minus decay, will move in this direction towards the valley of stability. Now, if we look at beta plus decay, if we start with a slope that's not very steep, and then this occurs, we lose a proton and gain a neutron. So the top decreases, the top increases, the bottom decreases. So this value gets bigger and our slope is going to get steeper. So we're going to move in this direction a little bit and our particle is going to move this way a little bit. And then looking at the graph, we have this region of beta plus decay. So if something over here undergoes beta plus decay, it will move in this direction towards the valley of stability a little bit. The big thing we want to be able to recognize is that if I have a nuclide whose neutron to proton ratio is too high, if it's off the valley of stability this way, then beta minus decay allows that ratio to approach a more stable value. And the same is true when the ratio is too low. We can undergo beta plus decay to move it in this direction. So you could imagine electron decay will occur in this region as well. So those are the big questions that we wanted to ask with relation to the nuclide chart. A couple other things we want to make note of is that beta decay will change the atomic number and therefore the identity of the element because it changes the number of protons. So remember when we first introduced nuclide notation, we talked about the fact that the atomic number, which is the number of protons, is what determines the element that we're looking at. So if that number of protons changes, then we know that the identity of the element changes. So beta decay does just that. So earlier today, we said that the proton number changes by plus or minus one because it could either gain or lose a proton. But then recognize that the number of neutrons is also going to increase or decrease. And if we gain a proton, we also lose a neutron. If we lose a proton, we also gain a neutron. So the total mass number, which is the number of protons and neutrons, is going to stay the same when we undergo beta decay. We're not seeing a change in the mass of the particle, but we are seeing a change in the identity of the element. So when we talked about stability, we said that whether a given nuclide is stable or not depends on the number of protons and neutrons. So we could have two particles of equal mass, but one is more stable than the other just because of the number of protons. And because the number of protons corresponds to the identity of the element. The same idea is true where a nuclide could be stable or unstable with the same mass number depending on the element. So beta decay is not affecting the amount of mass, but it is affecting the identity of the element. And it's changing it to something that would be more stable with that same mass number. Okay, and then I just want to reinforce that what beta decay is doing on a big conceptual level is it's moving them on this graph towards this valley of stability, where all of the stable nucleides are. So just to review our learning goals for today, we said we wanted to review beta minus decay and beta plus decay. And after that, we got into neutrinos and we wanted to understand the role of the neutrino in conserving energy and momentum. So we did that and we talked a little bit about the historical background. Then we also introduced electron capture and we talked about the differences between it and positron emission and recognize that positron emission is just beta plus decay because the positron gets emitted. And then right at the end, we talked about beta decay changing the identity of the nucleus and therefore affecting nuclear stability. So it looks like we covered everything that we wanted to, and that wraps it up for this lesson.